All right, let's talk about one of the biggest ideas in all of science, quantum mechanics. But here's the thing. It didn't just show up one day as some grand, perfect theory. Nope. It was born out of total crisis. It was a series of desperate, kind of crazy fixes to problems that classical physics just could not handle. So today, we're going to explore how three totally baffling puzzles didn't just bend the old rules, they shattered them, and then rebuilt our entire picture of reality from the ground up. So how did this all go down? How did a few weird results from a few experiments, puzzles that made absolutely no common sense, end up sparking a revolution that now powers everything? I mean, from your computer to lasers to how we understand the entire universe. That's the big question we're diving into right now. So our story kicks off at a time when physicists were, let's just say, feeling pretty confident. We're at the very end of the 19th century. Yeah, physicists at the time really thought they had it all figured out. They had Newton's laws for how things move. They had Maxwell's equations for light and electricity. The universe just seemed like this giant, predictable machine. You know, they figured they were just dotting the I's and crossing the T's. But one of those little loose ends was about to unravel everything. Okay, so the very first crack in this perfect picture came from something super simple: heat. According to the old rulebook, any hot object, think of a poker heating up in a fire, should be blasting out energy at all frequencies. But the math said that at the high energy end, the ultraviolet part of the spectrum, it should release an infinite amount of energy. Now, this was so spectacularly wrong, it got this awesome, dramatic name: the ultraviolet catastrophe. Because in the real world, the energy goes up, it peaks, and then it falls back down, which is good because it saves the universe from just poofing out of existence. But nobody had a clue why. What was stopping it? And this is where our first hero comes in, a German physicist named Max Planck. And what's so fascinating is he really didn't want to start a revolution at all. Planck banged his head against this black body problem for years, trying to make it work with the old physics, and he just kept failing. So finally, as he put it, in an act of desperation, he tried something that went against literally everything he and every other physicist thought they knew about how energy worked. And this is the core of his wild idea. Planck suggested that maybe energy isn't like a smooth, continuous ramp. He said, what if it's quantized, meaning it can only be given out or taken in these tiny, separate packets he called quanta. It's really just the difference between a ramp and a staircase, right? You can be on step 1 or you can be on step 2, but you can never, ever be on step 1.5. He basically said energy works the same way. Now, as weird as this idea was, it produced something incredible. The moment Planck put quantized energy into his equations, introducing his now famous constant, the math just worked perfectly. His formula lined up exactly with all the real-world data. But even Planck was really uncomfortable with it. He thought, maybe this isn't a new law of nature. Maybe I just found some clever math trick to get the right answer. So was it just a math trick? Well, 5 years later, this young, completely unknown patent clerk in Switzerland, you might have heard of him, Albert Einstein, he argued that no, it was very, very real. And he used it to solve a totally different puzzle. And this brings us to puzzle number 2, the photoelectric effect. This was something people knew about. You shine a light on a piece of metal, and sometimes it knocks electrons right off. But here was the super weird part. For any metal, only light of a certain color, or frequency, would actually do the job. A really dim blue light could pop electrons out, but a super bright, intense red light would do absolutely nothing. Now, if light was a wave, which is what everybody thought, a brighter wave should have more energy and should always work. So classical physics was just stumped. Einstein is the one who connected the dots. He took Planck's act of desperation and said, okay, what if we apply this to light itself? What if light isn't a continuous wave? What if it's actually made of those little energy packets Planck was talking about? He called them light quanta, which we now call photons. In this picture, light is basically a stream of tiny particles. And, this is the key, a single photon's energy depends only on its color, its frequency. Brightness just means you're getting hit with more photons, not more powerful ones. And just like that, Einstein's idea explained the whole puzzle. To knock an electron out, it has to get hit by a single photon that has enough oomph. A photon of red light just doesn't have the energy, no matter how many of them you throw at it. It's kind of like trying to knock over a bowling pin with a ping pong ball. It doesn't matter how many you throw at it, it's not going to work. And this whole idea got locked in years later, when the Compton effect showed photons literally bouncing off electrons and transferring momentum, just like tiny billiard balls. Planck's weird idea? It was real. Okay, so the quantum revolution now has two huge wins. But the third puzzle it had to solve was maybe the most fundamental one of all: the atom itself. I mean, why does anything exist?
Let's just quickly trace the problem. We started with the plum pudding idea, and then Rutherford came along and discovered the atomic nucleus. His experiments showed that an atom is mostly empty space with these tiny electrons orbiting a dense center, kind of like a mini solar system. It was a brilliant model, but it had a fatal flaw. You see, according to classical physics, an orbiting electron is always accelerating, so it should constantly be giving off energy as light. And losing all that energy means it should spiral down into the nucleus in like less than a nanosecond. So according to the old rules, atoms shouldn't be stable. They should collapse instantly.
So then comes the Danish physicist Niels Bohr, and he takes this quantum idea and applies it right to the structure of matter itself. He basically just throws out the old rules and makes three new, incredibly bold ones. Rule 1. Electrons can only exist in specific, allowed orbits and absolutely nowhere in between. Rule 2. While they're in those special orbits, they are perfectly stable and they just don't radiate energy. They simply break the classical rules. And Rule 3. Electrons can jump between these orbits, but only by absorbing or spitting out one single photon whose energy exactly matches the gap between those orbits. He called them quantum leaps.
The absolute genius of Bohr's model was how it explained this really old mystery. For ages, scientists knew that when you energize a gas, like hydrogen, it doesn't glow with a full rainbow. It only emits light at these very specific, sharp lines of color. It's like a unique barcode for every single element. Bohr's model finally showed why. Those lines of color? Those were the photons being spat out as electrons leaped down between the atom's different allowed energy levels. And his math for the hydrogen spectrum? It was unbelievably accurate. So let's pull all of this together. We had three separate, totally mind-bending puzzles and three bizarre, out-of-the-box solutions that, when you put them all together, painted a picture of a brand new and deeply strange reality. It all started with Planck, right? He was basically forced to quantize energy just to solve that black body problem. Then Einstein comes along and quantizes light itself to figure out the photoelectric effect. And finally, Bohr takes that same idea and quantizes the actual structure of the atom to explain why matter doesn't just collapse. You see the pattern here? It was powerful and it was undeniable. So what's the big takeaway from all this? The huge shift is this. Down on the smallest scales, reality is not smooth and continuous. It's fundamentally chunky. It's discrete. Energy, matter, light, it all comes in these tiny, indivisible packets called quanta. Light has this bizarre double life, acting like both a wave and a particle. And the rules that run this tiny world, they're all about probability and weirdness, not the predictable clockwork of the old physics.
This whole story, from Planck's desperate move to Bohr's impossible atom, it's a huge reminder that our common sense is really just a set of rules that happens to work on our big human scale. The quantum revolution proved that the real laws of nature are way stranger and, honestly, way more wonderful than we ever could have dreamed up. Which leaves us with a final question to chew on. What common sense idea that we hold about our universe today is just waiting for the right puzzle to come along and completely shatter it? Thanks for watching.